Hello everyone, my name is Kunal. Welcome to topic 3 of our statistics fundamental series. We have built a solid foundation with descriptive statistics and probability fundamentals. Now we are diving deep into one of the most powerful concepts in all of the statistics, the normal distribution, and how to work with it using the z-scores. By the end of this video, you will understand not just how the Bell curve works, but how to use it to solve the real world problems. You will be able to standardize data, calculate probabilities, and recognize normal distributions everywhere in the world around you. So let's begin. Let me start with why I believe the normal distribution is the most important distribution to understand deeply. In my 2 decades of working with data, I have found that understanding normal distribution separates a competent data analysts from those who just push the button in a software. Here are the key reasons. First, most natural phenomena follow normal distribution. You take heights of people, test scores, measurement errors, IQ, it's everywhere. Second, central limit theorem ensures sample means are normal. Even if the underlying data is not normal, the distribution of the sample means will always be normal. This is why normal distribution matters even when data doesn't look normal. Third, the normal distribution forms the basis of hypothesis testing and confidence intervals. Nearly every statistical test assumes normality. Understanding it deeply makes those tests intuitive. Fourth, z-scores enable standardizations. You can compare heights to weights or test scores across different subjects, apples to apples using z-scores. This power comes from understanding the normal distribution. Fifth, z-score lets you calculate probabilities. With one formula, you can answer what percentage of data falls in this range, and that is incredibly useful. Now let's look at the key properties of normal distribution. The normal distribution has specific mathematical properties that make it so useful. Let me walk through them. First, it's bell-shaped and symmetric. So if you fold the curve down the middle at the mean, both sides will match perfectly. This symmetry means mean, median, mode all are identical and they are at the center. Second, it's completely defined by just two parameters, mean and standard deviation. That's all you need. Tell me a mean and standard deviation and I can describe the entire distribution. This is elegant mathematics. Third, the total area under the curve equals 1. This represents 100% probability. All possible values sum to certainty. It's a continuous probability distribution. Fourth, the curve is defined mathematically. There is an actual equation which we call the probability density function that generates this shape. We don't need to memorize it, but it exists and is perfectly predictable. Fifth, the tails extend to infinity, but probability becomes negligible. Theoretically, nothing is impossible. You could be 10 feet tall, but practically the probability of you being 10 feet is so small that it's close to zero. This is why we say data is approximately normal, even though theoretically it can extend infinitely. These properties combine to make normal distribution incredibly powerful. Now I want to introduce what I call the most important rule in all of statistics, the 68-95-99.7 rule, which is also known as empirical rule. This rule tells you exactly where data concentrates in a normal distribution. 68% of the data falls within one standard deviation of the mean. So if your mean is 100 and standard deviation is 15, 68% of your data will fall between 85 and 115. 95% of the data falls within two standard deviations. For the same example, 95% falls between 70 to 130. This is why two standard deviation is often used as an outlier threshold. 99.7% falls within the 3 standard deviations. For our example, 99.7% falls between 55 and 155. Anything beyond 3 standard deviation is genuinely considered as an extreme. And here is why this matters practically. If you know something is normally distributed and you know its mean and standard deviation, you instantly know where almost all the data is. No fancy calculations are required. This rule appears constantly in real-life applications. In manufacturing, 3 sigma quality control means 99.7% of the products are acceptable. In medical testing, values beyond 2 standard deviation are flagged as abnormal. Please memorize this rule, understand it deeply. It's your shortcut to probability calculations. Now, what is a z-score? Now, let me introduce z-scores or z-scores, which are the practical tool for working with the normal distributions. A z-score is beautifully simple. It measures how many standard deviations a data point is from the mean. The formula is z-score, z is equal to x minus mu divided by standard deviation, which is sigma, where x is your data point, mu is the mean, and sigma is your standard deviation. So what this does to standardize your data? It converts any value into units of standard deviation. Here is the interpretation. Z-score equal to 0 means your data is exactly at the mean, perfectly average. When it's 1, it means your data point is 1 standard deviation above the mean. It's better than average. When it's minus 2, means your data point is 2 standard deviations below the mean, much worse than the average. A z-score of 2.5 means your data point is 2.5 standard deviation above the mean, which is quite extreme. What is the beautiful part of this? Every normal distribution can be converted to z-scores. Whether we are talking height in feet, weight in pounds, test scores out of 100, it really doesn't matter. Convert to z-scores and you can compare them all. This is why z-scores are so powerful. They are the language of standard comparison. Now let's look at an example where we will calculate the z-score for SAT scores. Let me give you a concrete example to make z-scores real. SAT scores are normally distributed with a mean of 1000 and a standard deviation of 200. These are actual statistics. Now imagine a student scores 1300 on the SAT. What is their z-score, right? Using the formula, z is equal to 1300 minus 1000 divided by 200, we end up with 1.5. So this student's z-score is 1.5. But what does this mean? Their score is 1.5 standard deviations above the mean. So which means they have performed 1.5 times sigma better than average. Using the 68, 95, 99.7 rule, we know that 68% of the students score within the plus or minus 1 sigma, which is between 800 to 1200. The student is actually scored beyond that and is in the top third of the top tier. More precisely, using a Z score table, Z score of 1.5 corresponds to approximately the 93rd percentile. So this student has actually outperformed about 93% of the test takers. This is incredibly useful information from a single calculation. In moments, we know not just the score is 1300, but exactly where it ranks relative to everyone else in the sample. This is the power of Z scores. They instantly translate raw scores into meaningful comparisons. Now let's talk about standardization and comparison. One of the most powerful applications of Z-score is standardization, which means allowing us to compare data on completely different scales. Here is an example I really love using. Imagine two students getting different test scores. Student A gets 92 out of 100 on a math test. The class mean is around 85 and standard deviation is 5. So the Z-score comes out to be around 1.4. Whereas student B gets 88 out of 100 in an English test. The class average is around 80 with a standard deviation of 4. So the Z-score comes out for student B close to completely, sorry, it's perfectly 2. Now here is the question, which student actually performed better? Your first instinct might say student A, they got 92 versus 88. But look at the Z scores. Student B has a Z score of 2, whereas student A has a Z score of 1.4. So clearly student B performed better even though their raw score was actually low. Why? Because student B was 2 standard deviations above their class mean, while student A was only 1.4 standard deviations above theirs. In student A's class, 85 is pretty good. In student B's class, 80 is not competitive. So standing 2 standard deviations above an easier class is better than standing 1.4 sigma above the harder class, right? This is nothing but the standardization. Z scores let you compare apples to apples when the contexts are completely different. So once you have converted data to Z scores, you can use the Z table to find probabilities and percentiles. A Z table shows you the cumulative probability, basically the percentage of data below any Z score. Here are some of the key values. Probability of Z score less than 0 is 0.5. That is 50% probability because 0 is the mean. Exactly half the distribution is below the mean. Similarly, probability score of Z less than -1 is around 0.1587. This means 15.87% of the data falls below one standard deviation of the mean. In practice, you don't need to memorize the Z tables anymore. You use software or calculators, but understanding what they represent is actually crucial. Every Z score maps to specific percentile. High Z scores means high percentiles, means top performers. Low Z scores means low percentiles or bottom performers. Z equal to 0 means 58th percentiles, exactly the average. And this is how Z scores turn raw scores into meaningful rankings. Now let's talk about practical application of Z scores. We will take the example of quality control. Let me give you a real world example of manufacturing that shows how this works in practice. Let's say a beverage company has a bottling machine. Bottles are supposed to contain 500 milliliters of the beverage, but the machines have natural variation. The actual distribution is normal with mean of 500 ml and standard deviation of 2 ml. The question is, what percentage of bottles contain between 498 and 502 ml of beverage? Using the Z scores, for 498 ml, the Z score comes out to be -1. For 502 ml, the Z score comes out to be +1. So we are basically asking what percentage of data actually falls between Z equal to -1 and Z equal to +1. Using the 68, 95 and 99.7% rules, 68% of the data falls between plus or 1 minus standard deviation, right? So 68% of the bottles will contain beverage between 498 ml to 502 ml. Conversely, 32% contains either less than 498 ml or more than 502 ml. Now the company might ask what percentage of bottles contain between 496 ml and 504 ml. So again, if you calculate the Z scores for 496, it will come out to be -2, and for 504 ml, it will be +2. Using the rule, 95% of the data will fall between plus and minus 2 standard deviations, right? So 95% of the bottles are within this range. So which means only 5% are defective. This is how quality control works in practice. Understanding normal distribution and z-scores lets manufacturers make decisions without testing every single bottle of the beverage. So now, what if the data is actually not normal? And a practical question that I get constantly is, what if my data isn't perfectly normal, right? So here is the good news. Small deviations from normality don't actually ruin your analysis. Normal distribution methods are quite robust. If your histogram looks vaguely bell-shaped, you can probably proceed without any hesitation. But here are your options. First, check for normality. Create a histogram to visualize. You can use a QQ plot to compare to theoretical normal distribution or use statistical tests like Shapiro-Wilk test. Second, understand that many real data sets deviate slightly, and that's okay. Statistical methods are resilient to minor non-normality. Third, if the data is severely non-normal or highly skewed or heavy-tailed, you have options. You can transform the data. Log transformations are very common for right-skewed data. Square root transformations work too. And after transformation, the data usually becomes more normal. Also, you can use non-parametric tests. These tests don't assume normality. They are less powerful, but they work with any distribution. Fourth, remember the central limit theorem. Even if raw data isn't normal, sample means are approximately normal. So, if you are working with sample means, which you usually are, normality will be a less of a concern for you. So here is my practical advice. Check for gross violations of normality. If your data looks reasonably symmetric, proceed. If it's extremely skewed or has outliers that concern you, transform your data or use non-parametric methods. Now let me show you how z-scores connect to hypothesis testing, which is where real statistical power comes from. Hypothesis testing uses z-scores to answer this question. Is my observed result unusual enough to be statistically significant? Now here is the process. First, you convert your data to z-scores for standardization. This kind of puts everything on the same scale. Second, you calculate a test statistics, often a z value, that measures how different your sample is from what you would expect under the null hypothesis. Third, you use the z value to calculate the p value. This is the probability of observing your data if the null hypothesis is actually true. Fourth, you compare the p value to your significance level. Usually, we take a significance level of 0.05. And if your p value is below that, the result is statistically significant. So here is the key insight. Larger absolute z-scores mean more extreme results. A z-score of 3 is way more unusual than a z-score of 1.5. Z-score of 2 roughly corresponds to a p-value of 0.05. That's why 2 standard deviation or 2 sigma is so common as a significance threshold. Z-tests are simplest hypothesis tests. They directly test whether a sample mean differs significantly from a hypothesized population mean using the z-scores. Everything that follows in hypothesis testing builds on this foundation. So now let me summarize the key formulas you need to know for working with normal distribution. The z-score formula is fundamental, which is nothing but your observation minus the mean divided by the standard deviation. This converts any value to standard deviations from the mean. The reverse formula is also equally important. Finding x given a z-score, which is nothing but x equal to mu, which is your mean, plus z-score multiplied by your standard deviation, which is sigma. This is useful when you want a certain percentile and need to find the actual value. Remember the 68, 95, 99.7% rule. These aren't approximations. They are precise for normal distributions. Now here are some Z-score interpretations. Uh, Again, these formulas and relationships are your toolkit for working with normal distributions. Master them. You can solve almost any normality related problem using this. Now let me walk you through several real-world applications where normal distributions and Z-scores appear constantly. IQ scores. IQ is designed with a mean of 100 and standard deviation of 15. A score of 130 is Z-score of 2. That's the top 2.3% of the population, which is why an IQ of 130 plus is often used as a gifted threshold. Medical testing. Doctors use normal distribution to identify abnormal lab values. If normal cholesterol is 200 plus or minus 40, then a reading of 280, which is a Z score of 2, which flags as abnormal and prompts investigation. Similarly, you have applications in finance, manufacturing quality control, weather and climate, and sport analytics. These are not theoretical applications, they are happening constantly in real business and science. Now, let's talk about the key takeaways. Let me crystallize the most important lessons from this topic, right? First, normal distribution is everywhere. It's not just in textbooks. Most natural phenomena, most measurements, most processes follow normal distribution. Second, the 68, 95, 99.7% rule is your shortcut. Memorize it, apply it. It answers most practical questions instantly. Third, one Z-score formula unlocks everything. Memorize this, understand it. It's the key to working with normal distributions. Fourth, Z-scores enable standardization. You can compare anything to anything, test scores, height, weight, stock returns, just convert them to Z-scores. Fifth, Z-scores are the bridge to hypothesis testing. Everything that follows in statistical inference uses Z-scores as the foundation. Sixth, recognize normal distribution is everywhere. Once you start looking, you will see them in data everywhere. Heights in your office, salaries in your company, temperatures throughout the year. You will observe normal distribution everywhere. Master these concepts and you have unlocked a key to statistical thinking. So thank you for working through the normal distribution and Z-scores with me. This is where the statistics actually becomes very powerful. In the next video, we will explore sampling distributions, how sample statistics relate to population parameters. You will see central limit theorem in action and understand why larger samples are more reliable. If you found this video useful and valuable, please like, subscribe, and comment. I usually read every comment and value your feedback. See you in the next one. Thank you.